Today we're going to look at section 6.5, which is all about the trig equations. So we're going to find all solutions of a trig equation today. A trig equation is an equation that contains a trig expression with a variable such as the sine of x. So an example would be if I wanted to know when the sine of x equals a half. So we're thinking about what is the angle measure that gets us that sine to be a half. Well, pi over 6 would work because the sine of pi over 6 is a half. So by contrast, pi would not be a solution because the sine of pi is 0, but we were looking for when it was a half. My question is pi over 6 the only solution when I was looking for that sine of x equal a half? And our answer is no. That takes us back to thinking about our graph. Remember, if I have a sine graph, it just keeps going and going and going. And if I'm specifically wanting to look at when we have the sine of x equals a half, well, notice that's what this maroon line is, or this purple line is. It's showing just in this small snippet of that graph, there was actually 5 solutions. Okay, so that essentially is telling us that we're going to have an infinite amount of solutions. So pi over 6 is not going to be the only thing that I want to write down. However, because something is an infinite, I can't actually list every single thing. So there's a way around that. We would say that our solutions are pi over 6 equals 2n pi, and that 5 pi over 6 plus 2n pi is our solution. So we would say these two answers, and then we have that plus 2n pi. So let me explain really quick why I selected those two out of this whole entire graph. If we're thinking about that phrase that all students take calculus, remember that phrase told us where our ratios were positive. And because we're talking about when sine of x equals a half, well, if we look at that, that would be in the first and the second quadrant. Okay, notice that pi over 6, that's a value in the first quadrant. 5 pi over 6 is a value in the second quadrant. So that kind of hits the first and the second quadrant. Now, why am I doing this 2n pi? Well, think about it. How did I get to 13 pi over 6? Well, if I took pi over 6 and I added 2 pi, which essentially think of it as 12 pi over 6, that takes me to 13 pi over 6. So technically 13 pi over 6 is back in the first quadrant. If I was to take 5 pi over 6 and add 2 pi, well, 5 pi over 6 plus 12 pi over 6, that's 17 pi over 6. So that's why that value is in the second quadrant. So all of these values are in the first or the second quadrant, and it's us adding 2 pi onto it. Now, the n tells us that if I just do 2 pi, that's one time around. But the n tells me that I could technically multiply that by 5. And so that means I went around the circle 5 times, or 100, and then I could go around the circle 100 times. So that's why we want this, this value and always added at the end of our solutions. So here are our steps and the thought process for solving an equation of these trig functions. First and foremost, we want to isolate the function on one side of the equation. Okay. After we've isolated, then we'll be able to solve for the variable. Once again, our answer then will be some kind of radian, and we're going to add that 2n pi onto it. So I want to use the unit circle as a reference here. So I'd always say, let's get out our unit circles. I have one attached if you couldn't find yours or you didn't bring it home. So use the unit circle to help you out with these problems. It says, let's find all solutions of the equation, the cosine of x equals the square root of 2 over 2. Notice that the cosine of x is already isolated by itself. So they already did step number 1 for us. So now we get to move on to the last step. We want to actually solve for x. Remember, cosine is the first number in our ordered pairs. So where do I see a positive square root of 2 over 2 first? I see it in the first quadrant, and I see it in the fourth quadrant. So that means that those are the values that we're going to want to use for x. In the first quadrant, that would be an angle value of pi over 4. But then remember, I always want to keep going back to that first quadrant, so I'm going to add 2n pi onto it. The other value is when we were in the fourth quadrant, and that's a value of 7 pi over 4. But to keep going back to then that fourth quadrant, once again, we want to add that 2n pi onto it. So these are all the solutions for when the cosine of x equals the square root of 2 over 2. If we're looking at trying to find when the tangent of theta equals negative square root of 3 over 3, well, tangent, you have to understand, is not already shown on the unit circle. You have to think about the fact that the tangent of x is the sine of x divided by the cosine of x. So we need to figure out, when am I going to have a tangent value be negative? That's only going to happen in the second and in the fourth quadrant, because that's where one of my values is positive in the ordered pair and one of them is negative. Now, because there's a square root of 3, that helps narrow down our choices. We want to deal with square roots of 3. So that gets rid of any ordered pair that has a square root of 2. But if I unrationalize this, think of it as negative 1 over the square root of 3. That'll help us see that this is really where we have 1/2 over the square root of 3 over 2, or technically one of them has to be negative. So negative 1/2 over the square root of 3 over 2. Because if I was then to reduce it down, it would get rid of the 2's, because we are multiplying the top and bottom by 2 to clear away those fractions. Okay, so that tells us that we have to have sine be either positive 1/2 or negative 1/2, and then vice versa. I need cosine to either be negative square root of 3 over 2 or positive square root of 3 over 2. And so like I said, that's going to fall in the second and the fourth quadrant. So that would be the ordered pair right here, and that would be the ordered pair right here. Okay, so if I'm looking at solving for theta, we know that that value is 5 pi over 6. And so then if I add my 2n pi, it'll keep taking me back to the second quadrant. If I look at the fourth quadrant, that would be 11 pi over 6. And if I keep adding 2n pi, I'll keep getting back to the fourth quadrant. Now, this is a little bit different, and we could actually shorten this even further. Notice this is the first time where our two potential answers are diagonal of each other. They are not two quadrants right next to each other. So notice there's actually a relationship between the second and the fourth quadrant and where those angles stand. Notice how they're actually half of the circle. So I could actually just say that my answer is 5 pi over 6, and instead of adding 2n pi, I could just add n pi. So that's telling me pi is half of the circle. So think about it. If I look at this, that is a semicircle, and so I could technically just say I'm going halfway around the circle each time, because then if I go from 11 pi over 6 and I add on pi, it'll take me back to the second quadrant. So it just keeps going around and around. So anytime you have something that is diagonal from each other, not right next to each other, you can add on just pi, and that will take you back and forth each time. Notice that in this problem, to find all solutions, I do not have my trig value isolated by itself. There's a sine of x on the left as well as the right. So I'm going to move that 3 sine of x over to the other side so I can start combining like terms. When I subtract, that gives me 2 times the sine of x equaling the square root of 3. And so I still don't quite have that sine isolated. I'm going to have to divide both sides by 2. And now I have my isolated trig function. So the sine of x equals the square root of 3 over 2. Remember, sine is second in my ordered pair, and I need it to be positive. Well, that falls here in the first quadrant, and that also falls right here in the second quadrant. Okay, so because those are two quadrants right next to each other, we're going to have to take each one individually, and we'll have to add on that 2n pi each time. So I do have two general solutions. I have to say that I have pi over 3 plus 2n pi, and that I also have 2 pi over 3 plus 2n pi. Once again, it's because those two quadrants are right next to each other. They're not diagonal. I can't add on just the n pi. I have to do each one individually. But then that hits each of those quadrants each time I keep going around the circle. Notice that in this next example, cosine is not isolated by itself, so I'm going to start rearranging terms so I can get that to happen. So that means I'm going to add 1 over to the other side. That gives me 2 times the cosine of x equals 1. So my last step to get the cosine by itself is I'm going to divide by 2. So the cosine of x equals a half. So if I'm looking for where my 1/2 is positive first in my ordered pairs, I will see that that's in the first quadrant, and it's also in the fourth quadrant. So because those are right next to each other, we are going to have to do each of those solutions individually. So I get a value of x to be pi over 3 plus 2n pi. Each time that will take me back to the first quadrant. I also have an answer of 5 pi over 3, where I have to add on this 2n pi so I can keep going back to the fourth quadrant each time as well. And those are my solutions. All right, what if I wanted us to find the cosine of x equals 0? Notice that it's already isolated by itself, so we don't have to worry about doing any type of manipulation. Notice that this time, when we're talking about 0, well, first in my ordered pair, that would be up here, and that would be down here. These are quadrantal angles. Notice that they don't fall within a quadrant, but because they are quadrantal, and one's on the top of my unit circle and one's on the bottom, notice how they are technically half of a circle away from each other, okay? And so because they are half of a circle away, instead of going 2 pi n and having to add each of those values one full rotation each time, this is the scenario where if I pick pi over 2, I can just add n pi, because by adding pi, that will take me to 3 pi over 2. Adding then pi again would take me back up to that pi over 2, which would then essentially be an even bigger angle next time. Okay, so this one, I just have to list that value once because we are dealing with half of a rotation each time we find that solution. All right, here is our last example. Notice that we do not have sine isolated by itself, so I'm going to subtract the sine of x to move it over to the other side. Combining like terms, that now gives me 2 times the sine of x equals -1. I'm going to divide both sides by 2, and so the sine of x equals -1/2. So I'm looking for, where do I have -1/2 second in my ordered pair? Well, that falls here in the third quadrant, as well as here in the fourth. Notice that those quadrants are right next to each other, which indicates we're going to have to do our solutions with 2 different angles. We start with the third quadrant, which is 7 pi over 6, and we'll add on that 2n pi, and then we move over to the fourth quadrant, where that would be 11 pi over 6, and we'd add on our 2n pi. All of these are solutions to that equation. All right, so that is us finding all solutions to these trig equations. I would like you to practice for homework page 637, numbers 11 through 23 odd, as well as 53.